In 1840s Vienna, giving birth in a hospital wasn't just risky, it was often deadly. In some years, over 15% of mothers died shortly after labor. That's 1 in 6 and like playing Russian roulette. But one young physician named Ignaz Semmelweis was about to change that, with an idea so simple it would save thousands of lives. And in this video, we are going to uncover what he did. We will look at real historical data from the Vienna General Hospital, where two clinics operated side by side. I'll show you the R code and good ways to visualize and analyze which clinic performed better. We will also explore which statistical test we can use to compare the clinics and assess whether the intervention from Semmelweis was effective and statistically significant. Here's the first data set. It shows birth and deaths for two clinics from the years 1841 till 1846. Clinic 1 was staffed by doctors and medical students, and Clinic 2 was operated by midwives. Looking at the table of raw numbers isn't the best way to judge which clinic did better, and even a bar chart of absolute numbers only helps a little bit. Let me show you what I mean, and then we'll look at better ways to clearly show the difference. If you are familiar with ggplot code, you notice 3 additional steps to produce either of these bar charts. First, we had to turn the yearly data into a long format, where the 2 columns for birth and death are converted into a category column. So with pivot longer, you create a category that now has both levels of birth and death and the associated value for both clinics. So you can see that for each clinic and year you have 2 values, one for the birth that happened in this clinic in this year and one for the number of deaths. And the ggplot needs this long format with 1 column for the categories you want to plot and the values associated. Secondly, without the facet wrap, both of these clinics would just overlap. I can show you this by adding a black outline around these charts, and you can see that clinic 1 and 2 are just stacked on top of one another with birth and death mixed together. So facet wrap helps you to untangle that. You can choose 1 row or 2 rows to plot it side by side or bottom top. You can choose the option to dodge the position of the columns, and one last thing was to change the levels so that death becomes red and birth green, and that also means that the births are now on the bottom of the stacked charts. Now the best way to do comparisons is to look at relative values or per capita ratios. And with mutate we can calculate the death rate or mortality by dividing number of deaths by total birth for that year. So here you have the proportion of deaths per birth. We can make it even more convincing if we turn it into a percentage format. And if we only select certain columns and use pivot wider, we can have the mortality rates side by side for the different clinics, and now it becomes quite obvious that Clinic 2 had a much lower mortality rate. Let me show you 2 more charts to hammer this point home. With a line chart and geom points, we can see that over the different years, the mortality was way lower in Clinic 2. The percent function from the scales package turns the y-axis into this nice percentage format, and with geom label you have a good way to print the actual mortality rates per year into the chart. And here you have a heat map that you can produce with geom tile function. It basically acts like a table with rows and columns, rows for years and columns for the 2 different clinics, and it has highlighted cells based on the values. So high mortalities get a red color and low mortalities are displayed in green. I won't go into the code here specifically because I will link to dedicated tutorials that I made on these different ggplot geoms. Now before we talk about what caused this discrepancy and how Semmelweis was able to lower the mortality for Clinic 1 even to lower levels than the one of Clinic 2, I want to do one more calculation. How can we estimate how many mothers would not have died prematurely if Clinic 1 had the same performance as Clinic 2? We can use group by for a specific column and then summarize to do all kinds of calculations. For example here, just add up all the birth and death that happened in Clinic 1 and Clinic 2 over the 6 years. And we can calculate the overall mortality by simply dividing these added up total numbers. And here you can see that Clinic 2 over 6 years performed at a 3.9% mortality rate, whereas Clinic 1 had 9.9%. Now if we take this average mortality from Clinic 2 and use it to estimate the number of deaths that Clinic 1 would have had, we get this number. And then we can calculate the excess death, so additional deaths that we get by subtracting this number from that. And the pull function extracts the values from this newly created column. And if we add them up, we realize that in this one clinic alone, over 1,200 women died unnecessarily because doctors did something wrong that the midwives got right. That is 200 women every year that weren't able to take care of their newborn child. Let me quickly describe the statistical test we can use to compare the different clinic performances and the success of Semmelweis' intervention. We are using the prop test in R, and you can use the help function or the question mark to get a full description of this test. In short, it compares proportions or rates between groups or against a fixed reference value. You provide two vectors, x and n, where x holds the counts of successes, in our case sadly the maternal death, so the event of interest, and one vector with the counts of trials, in our case the total number of births or deliveries. We can use group by and summarize to prepare these values for each clinic and feed them into the test. So the values were stored in results clinics, and with the $ and square bracket indices, I'm extracting the number of deaths for clinic 1 and 2 and the total number of trials or births for clinic 1 and 2. And if you hand over these short vectors that only have two values into the prop test, you get the following result. It calculates the mortality rates overall. These numbers we were already familiar with, we saw those, and it will give you the p-value and a 95% confidence interval. And the p-value tells us that giving this big sample size to find a difference of 10% compared to 3.9%, a rise from two clinics that, giving the null hypothesis being true, actually have the same mortality rate is effectively 0. And the 95% confidence interval estimates a difference of 5.5 to 6.5 percentage points between these two clinics. Now you have to be extremely careful if you do this test with a matrix approach. So here I took the exact same numbers as before and I created this matrix with named rows and columns. And you would expect if you hand over this matrix to the prop test to get the same results. But now all of a sudden the mortality rate is a little bit lower. And that is because these matrices for statistical tests don't want success versus trials, but outcome 1 versus outcome 2. So in our case, we have to subtract the number of deaths from the overall trials to get the two different outcomes of mother dying or mother surviving, which would add up to the total number of births giving in these clinics. And I stored this matrix in clinic mat2. And if you hand over this to the proportion test, now you get the exact same proportions as before, where we handed over two specific vectors. So keep that in mind. It's an important difference for these statistical tests. So now what exactly was causing this 6% gap? Clinic 2 was run by midwives focusing entirely on childbirth. Clinic 1, by contrast, was staffed by doctors and medical students, and here's the catch. These doctors weren't just delivering babies, they were also performing autopsies in the morgue and teaching anatomy classes. That meant frequent trips between corpses and laboring mothers, often without washing their hands. They unknowingly carried bacteria, the agents behind childbed fever, straight into the delivery room. And in a world without antibiotics, that was often a death sentence. One of the bacteria known to live on dead tissue in the pathology is Streptococcus pyogenes, describing bacteria that cause infections like strep throat, scarlet fever, and even necrotizing fasciitis. Don't Google images of that disease. The simple intervention that Semmelweis proposed was hand washing after autopsies and before assisting during labor. Not just with soap, but with disinfecting bleach, known as sodium hypochlorite or chlorinated lime. For the intervention analysis, we moved to the second data set that contains monthly data for the years 8041 till 8049 and is specific to Clinic 1, where hand washing was introduced in mid-May of 1847. So using mutate, we can calculate the mortality rate again, and we can flag pre- and post-intervention periods by asking whether the date is older than 1847 1st of June. So now we have an additional column that's logical, either true or false, before or after hand washing was introduced. Let us first plot the monthly mortality rates with the geom box plot and geom jitter. I have a tutorial on those as well. Be careful within jitter to set height to 0, otherwise the points will jitter in the Y direction as well, but we only want them to jitter horizontally. I use color and fill to indicate true and false hand washing intervention, and I like to use some alpha to make it a bit more transparent, and this looks already very promising, like the intervention worked. We can also create a bar chart again and use fill to indicate when the intervention happened. And here you see that many months were above 10%, some even reaching 20 or 30% mortality rate, and then it all plummeted to below 5 and on average to below 2%. If you want to create a line chart, you have to change geom col to geom line and then also change the fill to color, but then you get this break in between when the intervention happened. Still not a bad way to represent before and after changes. Finally, we can apply the proportion test again. So now we have total number of deaths and births before hand washing was introduced and after. Much smaller sample size, fewer years or months where we have these observations, but we can extract these values again and put them into vectors. And when we hand them over to the proportion test, we get 10.5% before hand washing was introduced and 2.1% after. So even lower values than the 3.9% we had for Clinic 2, and this difference is now estimated to be at least 7.8 to 8.9 percentage points better, which is roughly an 80% decrease. Now, unfortunately, this statistical test did not exist 170 years ago, and Semmelweis overall had a hard time convincing his colleagues to switch to hand washing. With these tests and evidence-based medicine and statistics and these charts, he would have had a much easier time convincing them to adopt this simple intervention. Many doctors refused to change their practices. After his death, mortality rates rose again, and today Semmelweis is remembered as the savior of mothers, a pioneer who championed evidence-based medicine against overwhelming opposition. Semmelweis used data to save lives, and today we can use it to learn, challenge assumptions, and maybe even change minds. If you want more stories like this that merge history, medicine, and analysis, leave a like or comment below. And if you're looking for hands-on support, tutorials, or help with your own data projects, check out my free school community where we dive deep into R and data analysis together. Thanks for watching, and I'll see you in the next video here at the Data Digest.